Have you ever wondered what lies at the center of the universe? Is there a core to everything we see in the cosmos, or is the idea of a center just an illusion? Scientists have long debated whether there's a specific point where the universe began, or if it stretches endlessly in all directions. Join me as we explore the theories about the universe's origins, what exists at its center, if anything, and how our understanding of space could change the way we think about everything around us. The cosmic axis of evil, a mysterious alignment in the universe, holds the key to answering these questions. In order to find the answer, we need to understand the mysterious alignment of the universe. You see, in the early 2000s, something strange emerged from the most detailed maps of the cosmic microwave background, CMB, the ancient light left over from the Big Bang. This light is a snapshot of the universe when it was only 380,000 years old, a glowing afterglow spread evenly across the sky. The CMB is an essential tool for cosmologists because it holds the key to understanding how the universe began and evolved. For decades, scientists believed this background radiation was almost perfectly uniform, with only tiny fluctuations that represented the seeds of galaxies and stars. But upon closer examination, an unexpected alignment was found, something that has come to be known as the cosmic axis of evil. The discovery of this mysterious axis didn't fit neatly into the framework of an isotropic universe. The name itself, Axis of Evil, comes from the fact that this alignment seemed to go against the randomness and uniformity that were expected. It felt like a cosmic anomaly. The axis of evil refers to a large-scale alignment of certain features in the CMB, specifically patterns that shouldn't have any particular orientation. Yet this axis suggests that these patterns are strangely aligned in a specific direction across the universe. It was as if the universe, instead of being entirely uniform, had a preferred direction, a finding that doesn't easily sit with the idea of an evenly expanding universe. So, what's going on here? Could this alignment be telling us something new about the nature of the cosmos? There are several potential explanations, ranging from more straightforward observational issues to the more mind-bending possibility of unknown forces or cosmic structures influencing the universe on a large scale. Some scientists argue that the cosmic axis of evil could be the result of observational bias or errors in the way the CMB data has been collected. The CMB maps are made by space telescopes, which, despite being incredibly advanced, are still subject to limitations. Perhaps the alignment is simply a coincidence, an artifact of the way the data was processed, or a quirk in the instruments used to measure the CMB. If that were the case, further observations and refinements to the data might make the alignment disappear. But the axis of evil has persisted through multiple datasets and observations, raising the possibility that it's not just an error. Could there be something more profound going on? Some researchers have proposed that this alignment could be caused by large-scale cosmic structures that we haven't yet fully understood. It's possible that massive structures like clusters of galaxies, or even more exotic forms of matter, could be exerting a subtle influence on the shape of the universe. These structures could be bending or warping space in such a way that the CMB appears aligned in specific directions. Another explanation might involve dark energy or dark matter, mysterious components of the universe that we still don't fully understand. Dark matter, which makes up about 27% of the universe, doesn't emit light or radiation, so it's invisible to us, but we know it's there because of its gravitational effects. Dark energy, on the other hand, is thought to be driving the accelerated expansion of the universe. Could these unseen forces be playing a role in shaping the alignment of the CMB? It's possible that the cosmic axis of evil might be a sign that these mysterious substances are influencing the universe in ways we've only begun to grasp. There are also more exotic theories. Some physicists have speculated that the cosmic axis of evil might hint at a deeper underlying structure or force that we don't yet fully understand. One idea is that the axis could be evidence of a violation of cosmic isotropy, the principle that the universe is the same in all directions. If this principle is not entirely correct, it would fundamentally change our understanding of the universe's geometry. Perhaps the universe is not as symmetrical as we thought. This could open the door to new theories about the shape and structure of space-time itself, including the possibility that our universe is part of a much larger, more complex multiverse. This idea, while speculative, has captured the imagination of some cosmologists. Could the cosmic axis of evil be a sign that our universe is influenced by forces beyond our observable reality? If we are indeed part of a multiverse, where different universes have different physical laws or structures, then it's conceivable that the alignment we're seeing in the CMB could be a reflection of interactions with neighboring universes or higher dimensional phenomena. While this is still very much in the realm of theory, it points to just how much we have yet to understand about the cosmos. What makes the cosmic axis of evil so intriguing is the impact it could have on cosmology itself. For decades, the idea that the universe is isotropic, that it looks the same in all directions, has been a foundational assumption in cosmology. If the axis is real and not just an observational error, it could mean that this assumption needs to be revised. A universe with a preferred direction would challenge some of the most basic principles of modern cosmology, forcing us to rethink how the universe evolved and how it continues to expand. This anomaly in the CMB data also highlights how much of the universe remains mysterious. Even though we've made incredible strides in understanding the cosmos, there are still deep unresolved questions that could upend our current models. The cosmic axis of evil may be one of those questions, pointing to an unseen pattern or structure that influences the entire universe. If it's real, this alignment could lead to new discoveries about the universe's origins, its ultimate fate, and the forces that shape everything we know. The cosmic axis of evil leaves us with a sense of mystery, a clue that the universe might be hiding something about its fundamental nature that we don't fully understand. This strange alignment challenges our assumptions about the uniformity and randomness of the cosmos. But beyond this anomaly, there are other ways the universe might be structured that could tell us even more about how everything works on the largest scales. While the idea of a cosmic center might be tempting, the overwhelming evidence from our observations suggests the universe doesn't have one. The expansion of space continues everywhere, stretching galaxies apart without any single point from which everything began. This ties into another fundamental question in cosmology: the shape of the universe itself. If we imagine the universe as a vast expanding entity, we naturally wonder about its overall form. Does it stretch out infinitely? Does it curve back on itself like the surface of a sphere? Or is it something else entirely? The shape of the universe. Understanding the universe's shape requires us to dive deep into the geometry of space itself and how it interacts with gravity, energy, and matter. There are three primary possibilities for the universe's overall shape: flat, open, and closed. Each of these shapes tells us something different about how the universe works and what might happen to it in the future. To begin, we need to think about the basic geometry of space. When cosmologists talk about the universe being flat, open, or closed, they're referring to how space behaves on the largest possible scales. A flat universe is one where parallel lines remain parallel forever, like on a flat piece of paper. In this model, space doesn't curve in on itself, and the overall geometry is Euclidean, meaning the rules of geometry we learn in school apply. A closed universe is one where space is curved like the surface of a sphere. In this model, if you travel far enough in one direction, you would eventually come back to your starting point, just like walking around the surface of the Earth. Lastly, an open universe is one where space curves outward like a saddle, and parallel lines eventually diverge. In an open universe, space continues expanding forever, and the further you travel, the more spread out things become. To figure out which of these models best describes our universe, once again, we have to turn back to the cosmic microwave background. By studying the patterns in this ancient light, cosmologists can measure the curvature of space. If the universe is flat, light from distant galaxies and the CMB should travel in straight lines. But if the universe is curved, that light will bend in predictable ways, depending on whether the universe is open or closed. One of the key ways scientists measure the universe's curvature is by looking at the size of certain features in the CMB. These features are fluctuations in temperature that represent the seeds of galaxies and other cosmic structures. In a flat universe, these fluctuations appear at a specific size, but if the universe is curved, the apparent size of these features changes, larger in a closed universe, smaller in an open one. By carefully analyzing the CMB, cosmologists have been able to measure the curvature of space with incredible precision. So, what do the measurements tell us? Based on the most recent data, it appears that the universe is very close to flat. This means that, on the largest scales, space doesn't curve much at all. It's not perfectly flat, but it's close enough that for all practical purposes, we can think of it as flat. This flatness has some important implications for the future of the universe. In a flat universe, space continues expanding forever, but at a slower and slower rate. Eventually, galaxies will drift so far apart that they're no longer visible to one another, but the universe won't collapse back in on itself. In a closed universe, by contrast, the expansion would eventually slow down, stop, and reverse. This would lead to a scenario known as the Big Crunch, where all matter and energy in the universe would collapse back into a single point, similar to how it all started with the Big Bang. In this model, the universe is like a balloon that expands to a certain point and then deflates. While the closed universe scenario is interesting, the current evidence doesn't support it. The data from the CMB and other measurements suggest that our universe is not curved enough to collapse in on itself. An open universe, on the other hand, would continue expanding forever, but at an accelerating rate. In this model, space would stretch so much that galaxies, stars, and eventually even atoms would be ripped apart by the relentless expansion. This scenario is sometimes called the Big Freeze or heat death, where the universe becomes so stretched out that all matter is spread thin and no new stars or galaxies can form. While this is a possible outcome, the data again suggests that the universe is much closer to flat than open. But what about the idea of a center in a flat or open universe? There is no center. Just like in the expanding balloon analogy, every point in the universe is moving away from every other point, but no single point is special. If you were to pick any galaxy in the universe, it would look like all the other galaxies were moving away from you. This is a consequence of the uniform expansion of space. In a closed universe, however, the geometry is different. A closed universe curves in on itself, like the surface of a sphere, and theoretically, this could imply some kind of central point. But this center wouldn't be located in our three-dimensional space. It would exist in a higher dimension outside of what we can observe. This makes the idea of a central point in a closed universe more theoretical than practical. The fact that we live in a universe that appears to be very close to flat also supports the idea that the universe is infinite. In a flat universe, space extends forever in all directions without looping back on itself. This means there's no edge to the universe and no center. While we can only observe a small portion of the universe, the observable universe, the actual size of the universe is likely much larger, possibly infinite. This has profound implications for our understanding of space and time. If the universe is infinite, there's no central point or edge, and the expansion we see is just part of a much larger, never-ending process. Hypervelocity stars, rogue stars fleeing from cosmic forces, are a remarkable and rare phenomenon, captivating astronomers because of the clues they offer about the universe's most extreme environments. Unlike the majority of stars that follow predictable orbits within galaxies, these rogue stars are ejected at such incredible velocities that they are flung beyond the gravitational grasp of their home galaxy, traveling alone through intergalactic space. Their existence raises fascinating questions about how they're accelerated to such speeds and what they can teach us about the hidden forces and dynamics at play in galaxies, especially near their most dangerous inhabitants, supermassive black holes. The discovery of the first hypervelocity star came in 2005 when scientists stumbled upon a star traveling so fast that it would eventually escape the Milky Way's gravitational pull entirely. This star, HV1, was found to be moving at over 1.5 million miles per hour, a velocity far greater than what would be expected from a star bound by the galaxy's normal gravitational forces. This revelation opened up new avenues of research into what could possibly accelerate stars to such extreme speeds. One of the key theories explaining the existence of hypervelocity stars is rooted in their interaction with supermassive black holes, the enormous black holes that reside at the centers of most galaxies. Our own galaxy, the Milky Way, harbors one of these titanic black holes, known as Sagittarius A*, which has a mass about 4 million times that of our Sun. When a star comes too close to a supermassive black hole, particularly if it's part of a binary star system, dramatic gravitational interactions can occur. A binary star system is a pair of stars orbiting each other. If such a system drifts too close to a supermassive black hole, one of the stars can be pulled into the black hole, while the other star is slingshot outwards at tremendous speeds. This process, known as the Hill's mechanism, is a type of gravitational slingshot effect. The energy from the interaction propels the remaining star outward with enough velocity to break free from the galaxy's gravitational pull entirely, sending it on a journey through the cosmos at breakneck speed. It's an extreme example of how supermassive black holes, typically known for their ability to trap everything, including light, can also have the opposite effect, flinging objects away at unimaginable speeds. The Milky Way central black hole, Sagittarius A*, is one of the primary suspects for the origin of hypervelocity stars in our galaxy. The extreme gravitational forces near Sagittarius A* are capable of disrupting star systems and ejecting stars. When astronomers discovered hypervelocity stars like S5 HVS1, one of the fastest stars ever detected, traveling at over 3.7 million miles per hour, they immediately suspected it had originated near Sagittarius A star. By tracing its trajectory back to the galactic center, scientists were able to strengthen this theory, confirming that these stars are often born near the chaotic heart of galaxies. However, binary interactions with black holes aren't the only way hypervelocity stars are born. Another possibility is through stellar collisions or interactions with other stars in dense star clusters. In regions of space densely packed with stars, such as the centers of globular clusters or near the cores of galaxies, close encounters between stars can also eject stars at high velocities. The gravitational tug-of-war in such crowded environments can occasionally fling stars outward. Although the velocities achieved in these scenarios are usually lower than those produced by interactions with supermassive black holes, interestingly, there's another lesser-known mechanism that can produce hypervelocity stars: supernova explosions in binary systems. If one star in a binary system undergoes a supernova explosion, the blast can propel the surviving companion star out of its orbit and into space at incredible speeds. The shock wave from the supernova, combined with the sudden loss of mass in the system, can impart enough energy to the companion star to send it racing away from its original location. While this process typically doesn't generate velocities as extreme as those seen in black hole interactions, it's still a viable way of creating hypervelocity stars. While these mechanisms explain how hypervelocity stars are ejected, studying these stars also offers a unique opportunity to investigate the extreme environments from which they come. In particular, hypervelocity stars act as probes of the supermassive black holes that ejected them. Since it's difficult to observe supermassive black holes directly, especially through the dense dust and gas that often surrounds them, hypervelocity stars provide an indirect way to study these cosmic behemoths. By tracking the paths and speeds of hypervelocity stars, astronomers can gain insights into the mass and behavior of the black holes that slingshot them into space. For example, the speed of a hypervelocity star can tell astronomers how close the star came to the black hole during its ejection. The faster the star, the closer it must have passed to the black hole. By studying multiple hypervelocity stars, scientists can map the gravitational influence of the black hole and learn more about its surroundings. This information helps to paint a more detailed picture of what's happening in the dense, energetic environments around galactic centers, areas that are typically shrouded in mystery. Beyond their relevance to black holes, hypervelocity stars also provide insight into the gravitational landscape of the universe. Once these stars are ejected from their home galaxies, they travel through intergalactic space, free from the gravitational bonds of any galaxy. This makes them excellent test subjects for studying the distribution of dark matter and other large-scale cosmic structures. As hypervelocity stars pass through different regions of space, they are influenced by the gravitational pull of dark matter and other galaxies. By tracking their paths, astronomers can glean information about the unseen forces at work in intergalactic space, helping to refine our models of how matter is distributed throughout the universe. Another fascinating aspect of hypervelocity stars is the potential for even more extreme cases, where entire star clusters are ejected from galaxies. While individual hypervelocity stars are rare, there is evidence to suggest that in galaxy mergers, when two galaxies collide, entire star clusters could be thrown out into space at high speeds. These hypervelocity clusters, if they exist, would be even rarer than individual hypervelocity stars. But they would provide further insights into the dynamics of galaxy collisions and the formation of large-scale cosmic structures. Moreover, studying hypervelocity stars in other galaxies may reveal more about whether these phenomena are common across the universe or unique to certain types of galaxies. In some cases, the sheer number of hypervelocity stars in a galaxy could point to an especially active or disruptive galactic core. For instance, galaxies with more frequent black hole mergers or more chaotic central regions might eject more stars than more stable galaxies. By comparing hypervelocity star populations in different galaxies, scientists can gain clues about the activity levels in various galactic environments. While much of the focus on hypervelocity stars revolves around their origins and their utility as probes of galactic dynamics, there's also an intriguing possibility. Could hypervelocity planets exist? If a hypervelocity star has planets orbiting it, those planets might be dragged along for the ride, carried into intergalactic space. Such planets, if they exist, would be nearly impossible to detect with current technology, but the idea raises fascinating possibilities about what kinds of worlds might be out there, far beyond the gravitational influence of any galaxy, traveling alone to the vast, empty reaches of intergalactic space. Primordial black holes, ancient giants at the universe's core, represent one of the most ancient and intriguing possibilities in cosmology. These black holes, unlike the ones we know that form from the collapse of massive stars, could have been born in the very first moments after the Big Bang. Their potential role in shaping the universe is fascinating because they might provide answers to some of the biggest questions in astrophysics, from the nature of dark matter to the formation of galaxies. In exploring the science behind primordial black holes, we enter into a realm where the physics of the very early universe meets the most extreme objects imaginable. The idea of primordial black holes begins with the chaotic, dense conditions that existed right after the Big Bang. During the universe's infancy, it was a hot, dense soup of particles, with energy fluctuating wildly on incredibly small scales. These fluctuations are key because they could have caused regions of space to briefly become so dense that they collapsed under their own gravity, forming black holes. This process is very different from how typical black holes form today, which happens when massive stars run out of fuel and their cores collapse. Primordial black holes would have formed within the first fractions of a second after the Big Bang, when the universe was still in its early stages of expansion. Unlike black holes formed by dying stars, which need to accumulate vast amounts of matter over millions of years, primordial black holes could have popped into existence in a matter of moments, thanks to intense fluctuations in the density of the early universe. Some theories suggest that these black holes could range in size from tiny, microscopic objects no bigger than a grain of sand to gigantic ones with the mass of thousands of suns. One key feature that distinguishes primordial black holes from their stellar mass counterparts is their potential mass range. Because primordial black holes formed in a very different way, their sizes could be much more diverse. Some might be so small that they have already evaporated due to a process called Hawking radiation, in which black holes slowly lose mass over time. Others, however, could still be out there undetected, lurking in the dark spaces between galaxies. The formation of primordial black holes depends on several factors, most importantly the density fluctuations in the early universe. These fluctuations were caused by quantum effects that stretched out as the universe rapidly expanded during a phase called inflation. In certain regions, the density might have been high enough to overcome the natural pressure forces that were trying to smooth out the universe's distribution of matter and energy. In these regions, gravity would have taken over, causing the matter to collapse into a black hole. What makes primordial black holes particularly intriguing is that they could have formed on scales much smaller than the size of galaxies. Some of these black holes could be the size of planets or smaller, while others could rival supermassive black holes in size. Their ability to form on such small scales opens up the possibility that they could have been incredibly numerous in the early universe, potentially influencing how structures like galaxies and stars formed later on. The role of primordial black holes in the universe's evolution doesn't stop at their formation. There is a possibility that they could act as hidden gravitational anchors, affecting the distribution of matter on cosmic scales. The gravitational pull of these black holes could have helped seed the formation of galaxies, acting as points around which gas and dust could collect. This clustering of matter is crucial to galaxy formation, and primordial black holes could have played a role in shaping the large-scale structure of the universe. If primordial black holes are numerous, their gravitational influence might help explain why galaxies are grouped together in clusters and why some regions of the universe have more matter than others. They could be responsible for the intricate web of cosmic filaments that stretch across the universe, connecting galaxies and clusters in a vast cosmic structure. In this way, primordial black holes might have shaped the universe, not by emitting light or energy, but by subtly guiding the movement of matter through their gravitational influence. One of the most tantalizing aspects of primordial black holes is their potential connection to dark matter, the invisible substance that makes up roughly 85% of the universe's matter. Dark matter doesn't interact with light, making it invisible to telescopes, but we know it exists because of its gravitational effects on galaxies and galaxy clusters. Some scientists have speculated that primordial black holes could account for at least part of this dark matter. If they are numerous and enough, these ancient black holes could make up a significant portion of the universe's missing mass, explaining the mysterious gravitational forces we observe in the cosmos. But detecting primordial black holes is no easy task. Unlike black holes formed by the death of stars, which often have observable effects like bright bursts of radiation when they consume matter, primordial black holes would be much more elusive. They might not have the same dramatic interactions with their environment, making them incredibly difficult to spot. Traditional methods of finding black holes, like looking for the X-rays emitted when they pull in nearby matter, might not work for primordial black holes. One possible method of detecting primordial black holes is by looking for gravitational lensing. Gravitational lensing occurs when a massive object, like a black hole, bends the light from a distant star or galaxy as it passes by. If primordial black holes exist in large numbers, we might be able to detect their presence by observing subtle changes in the light from distant objects. However, even this method has its challenges, as the lensing effects from small primordial black holes would be incredibly faint and difficult to distinguish from other cosmic phenomena. Another way to search for primordial black holes is by studying the gravitational waves they might produce. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as black holes merging with one another. In recent years, gravitational wave detectors like LIGO have detected the mergers of stellar mass black holes. If primordial black holes exist, they might also produce gravitational waves when they collide, though these signals would be different from those produced by larger stellar mass black holes. Scientists are actively looking for these signals, hoping to catch a glimpse of these ancient objects through the ripples they create in space-time. But perhaps the most exciting possibility is that primordial black holes could provide insight into the early universe's structure and the question of whether there is a core or central point in the cosmos. If these black holes formed shortly after the Big Bang, they could be some of the oldest objects in the universe, giving us a direct connection to the conditions of the primordial universe. Their distribution across the universe might offer clues about how the universe's large-scale structure came to be. Vacuum energy. At first glance, the term might seem contradictory. How can a vacuum, which we typically think of as empty, have any energy? Yet, in the world of quantum mechanics, even the emptiest regions of space are teeming with activity. This invisible energy, constantly fluctuating in and out of existence, plays a crucial role in the structure and evolution of the universe. From its connection to the mysterious force known as dark energy to its implications for the future of the cosmos, vacuum energy challenges our understanding of the fundamental nature of reality. Even when space is devoid of matter, it's far from empty. The vacuum of space, according to quantum theory, is filled with quantum fluctuations. These fluctuations occur because of the Heisenberg uncertainty principle, which states that it's impossible to know both the position and momentum of a particle with perfect precision. This inherent uncertainty leads to temporary bursts of energy that manifest as particles popping in and out of existence, called virtual particles. These particles only exist for fractions of a second before they annihilate each other, but during their brief lifetimes, they create a measurable amount of energy. This energy, known as vacuum energy, exists everywhere, even in the vast emptiness of intergalactic space. While virtual particles are short-lived, their constant fluctuations contribute to the overall energy of the vacuum. The idea that empty space contains energy may seem strange, but it has been confirmed through various experiments. One of the most famous examples is the Casimir effect, where two metal plates placed extremely close to each other in a vacuum experience a tiny attractive force due to the suppression of certain quantum fluctuations between them. This effect is a direct consequence of vacuum energy at work. But vacuum energy isn't just an interesting quirk of quantum mechanics. It may also play a fundamental role in shaping the universe itself. One of the most intriguing ideas in modern cosmology is that vacuum energy might be responsible for the accelerated expansion of the universe. Over the past few decades, astronomers have discovered that the universe isn't just expanding, it's expanding faster and faster. This acceleration is thought to be driven by a mysterious force called dark energy, which makes up roughly 68% of the universe's total energy content. Dark energy acts in opposition to gravity, causing galaxies to move away from each other at an ever-increasing rate. The nature of dark energy remains one of the biggest mysteries in cosmology, but many scientists believe that vacuum energy could be the key to understanding it. If vacuum energy exists throughout space, its effects could accumulate on a cosmic scale, pushing the universe apart more and more as space itself expands. This brings us to Einstein's cosmological constant, a term he introduced in 1917 as part of his equations for general relativity. At the time, Einstein was trying to explain why the universe appeared to be static, neither expanding nor contracting. To balance the attractive force of gravity, he added the cosmological constant, a term that represented a kind of repulsive force inherent to space itself. However, after Edwin Hubble's discovery that the universe is expanding, Einstein famously called the cosmological constant his greatest mistake and abandoned the idea. Yet decades later, with the discovery of the universe's accelerated expansion, the cosmological constant made a comeback. Today, it's considered one of the leading explanations for dark energy. In this context, the cosmological constant represents the energy of empty space, vacuum energy. Far from being a mistake, Einstein's idea might be central to understanding why the universe is expanding faster and faster. The energy of the vacuum, though tiny on small scales, could be responsible for pushing galaxies apart on cosmic scales. The implications of vacuum energy and its connection to dark energy are profound. If the accelerated expansion of the universe is indeed driven by vacuum energy, it raises questions about the fate of the universe. How the universe will evolve in the distant future depends largely on the properties of dark energy and, by extension, vacuum energy. One possible scenario is that the universe will continue to expand forever. If vacuum energy remains constant over time, the universe's expansion will never stop. Galaxies will continue to drift apart until they are so far away from each other that they are effectively isolated. Over billions of years, stars will burn out, galaxies will cease forming, and the universe will grow cold and dark in a scenario known as the heat death or Big Freeze. In this distant future, the universe will be dominated by dark energy, with all matter spread thin across an ever-expanding void. Another possibility is that vacuum energy might change over time. If the energy of the vacuum fluctuates, it could lead to different outcomes for the universe. In one scenario, dark energy could weaken, causing the expansion to slow down and eventually stop. In this case, the universe might reverse its expansion and begin to collapse, leading to a big crunch, where all matter and energy are pulled back together into a singularity, much like the state the universe was in before the Big Bang. However, there is another, more dramatic possibility: the Big Rip. In this scenario, dark energy doesn't remain constant, but instead increases over time. If the repulsive force of dark energy continues to grow, it could eventually overcome all other forces in the universe. This would cause not just galaxies, but stars, planets, and even atoms to be torn apart. The expansion of the universe would accelerate to the point where even the fundamental particles that make up matter would be ripped apart in the final moments of cosmic existence. The dark flow. For a long time, astronomers thought they had a good handle on how the universe behaves on these grand scales. Galaxies, driven by the expansion of the universe, should be moving away from each other more or less uniformly, unless their local gravitational environments, other galaxies or galaxy clusters nearby, alter their paths. But in 2008, something strange was observed that shook this understanding. A group of galaxy clusters, located billions of light years from Earth, seemed to be moving in the same direction, all headed toward a mysterious point beyond the visible universe. This phenomenon was named the dark flow, and it raised more questions than answers. What they found was unusual. These galaxy clusters, some of the most massive structures in the universe, were moving at an unusually high speed, roughly 600 to 1,000 kilometers per second, toward a specific direction. Stranger still, this motion wasn't just random. It was consistent across a vast region of space, suggesting that something was pulling these clusters in the same direction. This movement didn't fit with our understanding of how galaxies should behave. According to the standard model of cosmology, the universe is expanding, driven by dark energy, and everything within it is getting farther apart. But the galaxies and clusters within this dark flow seem to be moving toward a point far beyond the observable universe, where we can't see or measure what lies beyond. What could be pulling on these galaxies with such force? The answer, it turns out, is not simple, and it opens up the possibility that the universe is far more complex than we ever imagined. One possible explanation for the dark flow is that it's being caused by a large-scale cosmic structure that exists beyond the observable universe. The universe is filled with enormous structures, galaxy clusters, superclusters, and vast filaments of dark matter that form a web-like structure on the largest scales. These structures are shaped by gravity and influence the motion of galaxies and clusters. But the key limitation we face is that we can only observe part of the universe. The observable universe, which is defined by the distance light has traveled since the Big Bang. Beyond this boundary, light simply hasn't had enough time to reach us yet. However, just because we can't see beyond this cosmic horizon doesn't mean nothing is there. It's possible that the dark flow is caused by an unseen attractor, a massive region of matter or energy that lies outside our observable universe. This attractor could be pulling on the galaxies and clusters, dragging them toward it in a way that we can't fully explain based on what we currently know. While we can't observe this attractor directly, the motion of the galaxies and the dark flow gives us a clue that something is there, something massive and powerful enough to influence the movement of galaxy clusters over billions of light years. Some scientists suggest that this unseen attractor could be a supermassive structure, perhaps another region of space that is more densely packed with galaxies, dark matter, or some other form of matter that exerts a strong gravitational pull. Others speculate that this might even be evidence of a multiverse, the idea that our universe is just one of many, and that these other universes might be interacting with ours in subtle ways. If this were true, the galaxies in the dark flow could be feeling the gravitational influence of another universe that lies beyond the cosmic horizon, pulling them toward it with a force we can't directly observe. The idea that there could be something outside our observable universe that influences what happens within it is both thrilling and unsettling. If these massive structures or forces exist, they would challenge some of the core assumptions in cosmology. Our current model of the universe, which includes the expansion driven by dark energy and the formation of galaxies influenced by dark matter, would need to be reevaluated. Based on our understanding of the early universe, they seem to be hiding in a way that makes them difficult to detect. One promising theory suggests that these missing baryons are not in stars or galaxies, but rather spread throughout the universe in the form of diffuse gas. This gas would be too faint and too cool to emit much light, making it effectively invisible to the telescopes we currently use. However, it would still exert gravitational influence, meaning it's out there, shaping the cosmos in ways we can't easily see. This diffuse gas is thought to reside in the cosmic web, the vast web-like structure that connects galaxies and galaxy clusters across the universe. The cosmic web is a network of filaments, vast strands of dark matter and gas that stretch across the universe and link galaxies and clusters together. These filaments are some of the largest structures in the cosmos, stretching for hundreds of millions of light years. While dark matter forms the backbone of the cosmic web, it's believed that baryonic matter, particularly the missing baryons, might reside within these filaments as well, filling the spaces between galaxies in a diffuse, hard-to-detect state. If the missing baryons are hiding in these filaments, they wouldn't emit much light. Instead, they might exist as hot, ionized gas that is difficult to observe. This gas could be spread thinly across vast distances, making it nearly invisible to conventional telescopes. In fact, this theory has been supported by recent observations of X-rays and quasar light passing through intergalactic space. These observations suggest that there are indeed vast amounts of ionized gas filling the spaces between galaxies, potentially accounting for the missing baryons. One way to detect this faint gas is by using quasars, extremely bright, distant objects powered by supermassive black holes. Quasars emit intense light that travels across the universe, passing through clouds of gas on its way to Earth. By studying how this light is absorbed at different wavelengths, astronomers can detect the presence of gas that might otherwise be invisible. Some of this absorption appears to come from gas in the cosmic web, hinting that the missing baryons might be hiding in these diffuse clouds of ionized gas. Another key piece of evidence comes from X-ray telescopes. The gas in the cosmic web is thought to be extremely hot, millions of degrees, causing it to emit X-rays. Observations from space telescopes like Chandra and XMM Newton have detected faint X-ray emissions coming from regions between galaxy clusters, providing further evidence that hot, ionized gas is present in these filaments. This gas, while faint, could account for a significant portion of the missing baryons, helping to fill in the gaps in our cosmic inventory. The existence of these missing baryons in the cosmic web also helps to explain the large-scale structure of the universe. As the universe evolved, gravity pulled matter together into dense regions, forming galaxies and clusters of galaxies. But much of the matter in the universe didn't form into stars or galaxies. Instead, it remained in a more diffuse state, spread out along the cosmic web's filaments. These filaments act as highways for matter to travel along, connecting galaxy clusters and helping to shape the universe's structure. This hidden structure, composed of dark matter and diffuse gas, plays a crucial role in the evolution of galaxies. As gas flows along these filaments, it can fall into galaxies and feed star formation. In this way, the cosmic web not only connects galaxies, but also helps to fuel their growth. The missing baryons, if they are indeed hiding in these filaments, are an essential part of this process, acting as the invisible scaffolding that holds the universe together. The cosmic web's filaments also offer a clue as to how galaxies form and cluster together. When we look at the large-scale structure of the universe, we see that galaxies are not evenly distributed. Instead, they form clusters and superclusters with vast voids between them. These structures are shaped by the cosmic web, which acts as a kind of framework for the universe's growth. The missing baryons, if spread out in these filaments, would help to explain why galaxies and clusters form in these specific patterns, rather than being randomly scattered across space. Despite these advances, the search for the missing baryons is far from over. While there is growing evidence that they exist in the cosmic web's filaments, there are still many uncertainties about how much of this matter we've accounted for. Some of the missing baryons might still be hiding in other forms, such as cooler, less ionized gas, or even in the outer regions of galaxies that are difficult to observe. The Adenus supervoid. In the vast, intricate structure of the universe, most regions of space are filled with galaxies, stars, and other cosmic material. However, not all areas of the cosmos are equally populated. Some regions, known as voids, are strikingly empty, containing far fewer galaxies than expected. One of the most fascinating of these is the Adenus supervoid, an enormous region of space that appears to be unusually empty and cold. This supervoid is tied to one of the greatest mysteries in modern cosmology, a cold spot in the cosmic microwave background. The Adenus supervoid has become the subject of intense interest because of its possible connection to this cold spot. The CMB is remarkably uniform, but it has small fluctuations in temperature, tiny differences that reflect the conditions of the early universe. Among these fluctuations, one area stands out as being significantly colder than its surroundings. This CMB cold spot, located in the direction of the constellation Eridanus, is much colder than the standard models of the universe would predict. Scientists have been trying to understand what could be causing this anomaly, and the discovery of the Adenus supervoid in the same direction provides a potential explanation. At first glance, the existence of a cold spot in the CMB might not seem that surprising. After all, the CMB itself is not perfectly uniform, with small variations in temperature that are attributed to differences in density in the early universe. These variations are crucial for the formation of galaxies and other cosmic structures, providing the seeds around which matter coalesces. But the Eridanus cold spot is different. It's much larger and colder than other fluctuations, raising questions about what could have caused such an extreme anomaly. One leading explanation is that the Adenus supervoid, a massive region of space with far fewer galaxies and matter than expected, might be responsible for this cold spot. Supervoids are not uncommon in the universe. Voids of various sizes are scattered throughout the cosmic web, the large-scale structure of the universe. These voids are regions where the density of matter is lower than average, and they can span hundreds of millions of light years. But the Adenus supervoid stands out because of its size and the possibility that it is linked to the CMB cold spot. The relationship between the supervoid and the cold spot could be explained by a phenomenon known as the Sachs-Wolf effect, which involves how light behaves as it passes through regions of varying gravitational strength in the universe. When photons from the CMB pass through a supervoid, they encounter less gravitational pull compared to regions with more matter. As they enter the void, they are blue-shifted, gaining energy as they fall into the gravitational potential of the void. However, as the photons leave the void, they lose energy, becoming redshifted. This loss of energy can create a cooling effect, where the CMB photons that pass through the void end up with slightly less energy, making the region appear colder when viewed from Earth. In the case of the Adenus supervoid, the size of the void could be amplifying this Sachs-Wolf effect. As CMB photons travel through this vast, underdense region of space, they lose energy, resulting in the cold spot we see in the CMB. While this explanation fits well with what we observe, it's not yet definitive. The Sachs-Wolf effect alone might not fully account for the extreme coldness of this region, leading some scientists to speculate that other, more complex factors might be at play. One of the big questions surrounding the A-Dennis supervoid is whether it's a unique anomaly or part of a larger pattern of cosmic structure. Voids like this are an integral part of the universe's large-scale architecture. The cosmic web, which consists of galaxies, galaxy clusters, and dark matter, is interconnected by vast filaments of matter. In between these filaments are voids, regions where matter is much more sparse. These voids, including the A-Dennis supervoid, help define the shape and structure of the universe. But most voids don't produce such a pronounced effect on the CMB. So why does this one? One possibility is that the A-Dennis supervoid is part of a larger, more complex structure that we don't yet fully understand. Some researchers have suggested that it might be connected to other nearby voids, forming a kind of superstructure in the cosmic web. If this were the case, it could provide a clue about how the universe's large-scale structure evolved, offering insights into the nature of dark matter and the distribution of galaxies. This idea is still speculative, but it raises the intriguing possibility that the A-Dennis supervoid could be a piece of a much larger puzzle, one that could reshape our understanding of how matter is distributed throughout the universe. There's also the possibility that the A-Dennis supervoid might not be the only factor responsible for the CMB cold spot. Some theories suggest that the cold spot could be the result of more exotic phenomena, such as the influence of dark energy or even interactions with other universes. In some versions of the multiverse theory, our universe is just one of many, and the cold spot could be a sign of a collision or interaction between our universe and another. While this idea is highly speculative, it highlights how little we know about the fundamental nature of the cosmos and the forces that shape it. The discovery of the A-Dennis supervoid has prompted a re-examination of how voids and other large-scale cosmic structures influence the universe. Voids are fascinating because they provide a unique environment in which to study the effects of gravity and dark matter. In dense regions like galaxy clusters, the gravitational pull of matter is strong, and galaxies move according to well-understood gravitational dynamics. But in voids, where there is much less matter, the rules of cosmic evolution can play out differently. One of the key challenges in studying voids like the A-Dennis supervoid is that they are difficult to detect. Unlike galaxies or clusters, which emit light and can be easily seen with telescopes, voids are defined by what's missing. To find them, astronomers must carefully map the distribution of galaxies and look for regions where the density of galaxies is significantly lower than expected. The A-Dennis supervoid, for example, was detected by mapping the distribution of galaxies in the region and noticing a large area where very few galaxies exist. Despite these challenges, voids provide a wealth of information about the universe's structure and evolution. By studying how galaxies and matter are distributed in and around voids, scientists can gain valuable insights into the forces that shape the universe and its evolution over time. Cosmic structures. Voids also offer a unique way to test theories of dark energy, the mysterious force driving the accelerated expansion of the universe. In conclusion, the study of cosmic voids not only provides a deeper understanding of the universe's large-scale structure, but also presents an exciting opportunity to explore the nature of dark energy. These vast, underdense regions of space might hold the key to unlocking some of the most profound questions in cosmology. By studying how galaxies and matter behave in and around voids, scientists can test various theories about dark energy and its role in the universe's expansion. If you enjoyed this content and want to stay updated on the latest cosmic discoveries, don't forget to like, share, and subscribe to Cosmic Lens.